Welcome to the deep dive. Today, we're pulling back the curtain on something pretty fundamental but often invisible, BGP4 plus IC.
That's right.
Think of it like the internet's super smart GPS mapping out how your data zips across the globe.
Exactly. It ensures everything gets where it needs to go.
Yeah.
And BGP4 plus X specifically is crucial because it's built for IPv6.
IPv6, the next generation internet addresses.
Precisely. It's an evolution of the border gateway protocol we've used for years, but adapted for the modern internet scale.
Okay, so our mission today, really get under the hood of BGP4 plus IC. We want to unpack what's new, how it works, and why it's so vital for keeping us all connected.
Sounds like a plan. It's a fascinating piece of engineering.
Let's dive in. Okay, let's unpack this then. You mentioned IPv6. What exactly is BGP4 plus differentiating it from, say, the BGP4 we already had? What problem was BGP4 hitting?
Well, the core idea is the same. BGP4 Plus is still Border Gateway Protocol version 4, but it's the implementation specifically designed to handle IPv6 address families.
Ah,
Its job is distributing routing information between different autonomous systems. Think big networks like ISPs, corporations.
right, the building blocks of the internet.
Exactly. The big problem BGP4 faced was simple. It was built for IPv4, and we ran out of IPv4 addresses, or were very close.
The address exhaustion problem.
Yes. So BGP4 Plus builds on all the good stuff in BGP4, the policies, the path selection, but crucially adds the ability to handle IPv6 natively. It needed that to support the future internet.
So it's not just a patch, it's a necessary upgrade for IPv6. What are the key enhancements that make this possible?
There are a few core ones. First, obviously, is IPv6 unicast address family support. It just understands IPv6 addresses directly. Second, there's new network layer reachability information, or NLRI, specifically formatted for IPv6. This lets routers advertise IPv6 routes very precisely.
More detail in the routes.
Exactly. And third, the next hop attributes, basically the address of the next router in the path, can now be IPv6 addresses. It modernizes how paths are calculated for IPv6 traffic.
Okay, so it's really about making the whole routing system fluent in IPv6. Future-proofing, essentially.
That's a great way to put it. It ensures the backbone can handle the transition smoothly.
So before we get into the real nitty-gritty of neighbors and paths, how does someone even start setting this up? It sounds complex.
It requires a structured approach, definitely. You begin in what's called BGP global mode. This is where you set the general BGP behavior for the router.
Like the master settings.
Sort of, yeah.
Yeah.
You use commands like address family here to tell BGP which address types it should even pay attention to: IPv4, IPv6, maybe VPN routes.
Okay.
Or you might configure a confederation, which is a way to group several autonomous systems together to look like one big one. Helps manage complexity. These global settings define the overall rules of engagement for your BGP router.
And then you drill down specifically for IPv6, right, using the IPv6 unicast address family part.
Exactly. Once you're in that specific configuration mode, the commands apply only to BGP4 Plus and IPv6 unicast routes.
Ah, so it's layered.
Correct. Here you'd use commands like aggregate address that lets you combine, say, a bunch of smaller IPv6 network prefixes into one larger summarized route.
Oh, to keep the routing table smaller.
Precisely. It helps massively with scale. Or you might enable multipath here, which allows the router to load balance traffic if it finds multiple equally good paths to a destination using BGP. It's about fine-tuning for IPv6 traffic.
Now, for routers to actually swap this routing info, they need to know who to talk to. That's where neighbors come in, right? Like routers introducing themselves.
Yeah, kind of. BGP4 Plus neighbors are simply other BGP routers, we call them speakers, that you configure your router to exchange updates with.
Okay.
And you can set these up using either link local IPv6 addresses, which are only valid on a specific network link, or global IPv6 addresses, which are reachable across the internet. Gives you flexibility.
And how do you set that up?
Key commands would be neighbor update source, which tells your router which of its own interface addresses to use when talking to that neighbor. And crucially, neighbor activate. That command within the IPv6 address family actually turns on the exchange of IPv6 routes with that neighbor.
Right, got to flip the switch. Now, I imagine in a big network, configuring every single neighbor individually could get tedious.
Oh, incredibly tedious and error-prone. That raises a really important point about managing complexity at scale.
So how do network engineers handle that?
That's exactly why we have BGP4 Plus peer groups. They're a lifesaver.
Okay.
You essentially create a template, the peer group, and define all the common settings there, things like policies, timers, passwords.
Uh-huh.
Then you just assign individual neighbors to that group. They automatically inherit all those settings, configure once, apply many times.
Ah, that makes a lot of sense. Much cleaner.
Absolutely. And what's neat is a single peer group can even include both IPv4 and IPv6 neighbors if they share the same general policies. It really streamlines things in complex environments.
Okay, connections are made, groups are maybe set up. How do the actual routes get into BGP4 plus and then how do they get advertised out? Like gathering intel and broadcasting it.
Yeah, that's a good way to think about it. First, importing routes. A route must already exist in the router's main IPv6 routing table before BGP can touch it.
So the router needs to know how to reach it somehow first, like via an internal protocol or a static route.
Exactly. Once it's in the main table, you go into the address family IPv6 unicast mode and use the network command. You specify the IPv6 prefix, and that tells BGP, okay, I know about this network, you can advertise it.
Got it. So you explicitly tell BGP which known routes to share, and then advertising them, putting up that billboard.
Yep. A common thing is to advertise the default BGP4 plus route. You use the default information originate command.
And that tells everyone.
If you don't know where else to send your IPv6 traffic, send it to me. I'll figure it out. It's like being the gateway of last resort.
Useful for edge routers.
Very. And you can advertise that default route to all neighbors or just to a specific neighbor if you need finer control over traffic flow.
Right. Now this feels critical. How does BGP4 Plus figure out the next hop? The actual next device to send a packet to?
Ah, yes, the next hop.
Yeah.
This is fundamental. For any BGP4 Plus route to be considered valid and usable, the IPv6 address listed as its next hop must be reachable.
Reachable how?
Reachable according to the router's main routing table. Usually this means reachable via an interior gateway protocol, IGP, like OSPF-v3 or EIGRP for IPv6 something, running inside your own network. Or maybe a static route points towards it.
Okay, what if the next hop isn't directly connected or known by the IGP?
That's where BGP4 plus next hop recursion happens. The router basically performs a lookup for the next hop address itself. It asks, okay, how do I reach the next hop address specified in this BGP route?
It looks up the lookup.
Essentially, yes. It might even have to do this recursively, maybe a couple of levels deep, until it finds a path based on its IGP or static routes.
Yeah.
If it can't ultimately resolve that next hop address, the BGP route is useless, even if it learned it. The packet needs a concrete next step.
Okay, the internet is huge, constantly growing. These routing tables must get enormous. How do we stop routers from getting bogged down just looking up paths?
That is a massive challenge, and BGP4 plus route aggregation is the primary solution. It's absolutely vital.
Integration. Combining things.
Exactly. You take a block of more specific, smaller IPv6 network prefixes and advertise them as a single, larger, less specific prefix. For example, instead of advertising 256 small networks, you advertise one big one that covers them all.
Ah, I see. So fewer routes for other routers to process.
Dramatically fewer.
Yeah.
This reduces the size of the global internet routing table, saves router memory, speeds up lookups. I mean, without aggregation, the internet literally couldn't scale the way it has. Core routers would just collapse under the weight of millions of routes.
Wow. Okay, that's crucial. Now, multipath sounds interesting, using multiple paths.
It is. BGP4 plus multipath allows a router to use multiple, different, but equally good paths to the same destination at the same time.
For load balancing.
Precisely. Instead of sending all traffic down one pipe when you have several good options, it spreads the load, improves performance, uses bandwidth more efficiently, adds redundancy.
What makes paths equally good in BGP's eyes?
It checks several BGP path attributes, things like weight, which is a Cisco-specific value, local preference within your own AS, the origin of the route, the AS path length, how many networks it crosses, and sometimes the MED or multi-exit discriminator. If multiple paths are tied on these key attributes, multipath might kick in.
Gotcha. And route maps sound like creating custom rules for the road.
That's a perfect analogy. Route maps are incredibly powerful tools for implementing routing policy. You use them to influence BGP decisions.
How so?
You can match routes based on criteria like using an IPv6 prefix list.
Right.
And then set attributes or decide whether to permit or deny the route, either coming in, inbound, or going outbound.
So you can steer traffic.
Absolutely. You can prefer certain paths, filter out unwanted routes, modify attributes to influence neighbor choices, is how engineers implement business agreements, optimize traffic flow, and generally exert fine-grained control over how routes are handled.
Okay, moving beyond just path selection. What about more advanced control and especially security? This infrastructure is critical.
Very critical. One useful feature is BGP4 plus outbound route filtering, often called ORF.
Or RF.
Yeah.
Yeah.
It's a way for BGP neighbors to sort of negotiate what routes they don't want to receive. One router can send a prefix list to its neighbor saying, hey, don't bother sending me updates for these specific networks.
So the filtering happens before the routes are even sent?
Exactly. The neighbor filters them at the source. This saves bandwidth because the unwanted updates aren't sent. And it saves CPU on the receiving router because it doesn't have to process and then discard them. It's proactive filtering.
Clever. Then you mentioned BGP4 plus confederations earlier. How do they fit in? Dividing up big networks.
Right. Confederations are a way to manage really large autonomous systems. Imagine an AS so big that having every single internal BGP router talk directly to every other internal BGP router, what we call a full mesh IBGP, becomes impractical. Just too many connections.
Okay.
A confederation lets you break that massive AS into smaller sub-ASes. Within each sub-AS, you might still need a full mesh, but it's much smaller and more manageable.
And to the outside world.
To the outside world, the whole group still looks like one single AS number. It hides the internal complexity while making the internal routing scalable and preserving important BGP attributes across the sub-AS boundaries.
Makes sense for huge providers.
Mm.
And for security. You mentioned GTSM, like a bouncer.
Hey, yeah, generalized TTL security mechanism. It's a neat security feature mainly for external BGP, EBGP, the
Yeah.
connections between different autonomous systems.
How does it work?
It checks the time to live, TTL value, in the IP header of incoming BGP packets.
Mm-hmm.
Legitimate EBGP neighbors are usually directly connected or only one hop away.
Uh-huh.
So GTSM expects the TTL value to be very high, typically 255. If a BGP packet arrives with a low TTL, it probably came from further away, potentially an attacker trying to inject bogus routes or disrupt the session. GTSM can then just drop those packets.
Simple but effective. Protects against spoofing from afar.
Exactly. Helps prevent CPU overload attacks and session hijacking attempts on those critical inter-AS links.
What about stability? If one of these crucial BGP routers needs a reboot, maybe for maintenance or it crashes, does everything just stop? Does my connection drop?
Hopefully not. That's where BGP4 plus graceful restart is incredibly important.
Yeah.
It's designed specifically for service continuity.
How does that work?
When a BGP router supporting graceful restart needs to restart, it signals this to its neighbors. Those neighbors then don't immediately tear down the session and remove all the routes they learned from the restarting router.
Ah, they hold on to them.
Yes, for a period. They basically mark the routes as stale, but keep using them to forward traffic. Meanwhile, the restarting router comes back up, reestablishes its BGP sessions, and sends its routes again.
So traffic keeps flowing using the old information while the system recovers.
Precisely. The goal is to make the restart invisible, or nearly invisible, to actual data traffic. It avoids widespread disruption during planned maintenance or unexpected failures. It's all about resilience.
And you said this is usually on by default.
Often, yes, for both IPv4 and IPv6 address families in modern systems. It underscores just how vital it is for stable network operation.
Okay, we've configured global settings, address families, neighbors, peer groups, policies, security, graceful restart. After all that, how do engineers actually check if it's working? How do they troubleshoot?
Visibility is key. You absolutely need ways to display BGP4 plus statistics.
What kind of information can you see?
There are many useful commands. Show IPv6 BGP summary is a fundamental one. It gives you a quick overview. Who are your neighbors? Are the sessions up or down? How many prefixes have you received from each?
Like a dashboard?
Exactly, a quick health check. Then you can dive deeper. You can view the entire BGP table for IPv6, inspect the specific attributes of a particular route, see the configuration of peer groups, check exactly which routes a specific neighbor is sending you or which routes you're sending them.
So really detailed diagnostics.
Absolutely essential. These commands are how you validate your configuration, troubleshoot why a route might be missing or not preferred, check if policies are working as expected. It's how you keep the pulse of your BGP network. Without these tools, you'd be flying blind.
What an amazing deep dive. We've gone from the basics of BGP4 plus needing to handle IPv6 all the way through configuration, peering, optimization like aggregation and multipath, security with ORF and GTSM, and stability with graceful restart.
It really paints a picture, doesn't it?
Yeah.
BGP4 Plus takes the core power of BGP and extends it effectively into the IPv6 realm. It's all out enabling efficient, scalable, secure, and resilient routing for, well, the internet we rely on today. Advanced peering, route optimization, robust security, handling disruptions gracefully. It's all in there.
It truly highlights the incredible, often hidden engineering that makes our digital world tick. Every time you browse a website, send an email, stream a video, protocols like BGP4 Plus are working tirelessly behind the scenes.
Constant innovation, really.
Absolutely. And for you, our listener, here's something to think about. BGP4 Plus is foundational now, but what's next? Considering evolving threats, maybe quantum computing, breaking current security, or new types of cyber attacks, or even totally new ways of structuring the internet, how might protocols like BGP need to evolve again? What future challenges will shape the next generation of global connectivity, and what might those solutions look like?